Dr. Franklin Moon. He is a professor of civil engineering at Rutgers University.
It's a pleasure to be here this morning. This presentation is going to be a bit of a change of pace. I don't think I will mention drones, but we will talk about some emerging ways of collecting data and how that fits in with this new research tool. So before I get going, I need to acknowledge the New Jersey Department of Transportation, who partnered with Rutgers to develop the lab that I will talk about, and also Ali Maher, Nenad Kaczynski, and Dick Dunn, who have been helping us out as we're sort of trying to formulate how to use this lab. So sort of jump into it. So the some open questions, I say open, critical, and billion-dollar questions. First, what are the primary factors that lead to poor bridge durability? And how do we balance things like construction, or the influence of construction issues, structural characteristics, environmental, live load, de-icing agents? What are the best practices in design and maintenance actions to ensure long-term performance? What are the best techniques to identify deterioration early on, and then what are the best techniques to mitigate them, right? And a lot of people are surprised that these questions are still so open. In fact, a lot of people I talk to in different disciplines are really surprised because it seems like we should have been focusing on these things for a long time. So spoiler alert, first off, I'm not going to answer these questions today. We'll talk about a research approach that I think will help answer them. But I put this slide together. I don't know if you all would be interested in this, but it sort of fascinated me. I got hooked on this Ngram viewer from Google Books, and it seems very simple. Basically what it does is it plots the percentage of words published in English books that would correspond to certain terms. You can put any terms in there. So I put in bridge construction and bridge design here, and I'm plotting back from like 1840 to 2000, right? And so you can see this is sort of a surrogate for the perceived importance of these topics. And what's really interesting is you can start to look at what was happening historically, right? Pacific Railroad Act, Ford introduces the Model T. World War I think this actually here is just, you know, the publication of books lags a bit, right? They're written before they're published. So this is sort of, you know, when people were focused on the war, Great Depression, Federal Highway Act, AASHTO LRFD, we started to talk about design about as much as construction. I love that we talk about construction, you know, 20, 30 years before people started talking about design. But if you then start to look at other terms like bridge management, look at when people started to write about bridge management, right? Late 80s, right? Bridge rehabilitation, right? It's just peaking up there. And bridge preservation, which I know is near and dear to all of our hearts, it's not even a thing in 2000, right? And I've tried bridge maintenance. There's a lot, you can play around with these terms, right? And there's a lot of confirmation bias that you can get from these sort of things. But I think the point is that for a long time, people were focused on designing really good bridges and building really good bridges. And I would argue that a lot of those problems have been solved. And, you know, over the last 15 years, granted this only goes to 2000, 15, 18 years, there's been a shift and there's a lot more focus on bridge preservation. And I think that's a sign of a sort of maturing infrastructure system, right? So let's structure bridge performance, right? And this is the way that, you know, over the last few years, we've begun to start thinking about this as a bridge system, or any system, can be described based on its attributes, sort of its inherent characteristics, age, design details, materials, construction quality, all that stuff that sort of makes up the system. And then inputs to that system that come from the outside. And they can be environmental, live load, maintenance, you name it, right? And then there's a function that translates those inputs and attributes into certain performance measures. And that can be as simple as a condition rating, or it can be a measure of structural safety or functionality or cost, or however you want to describe performance. But in general, bridge performance research should aim to try to compute this function, right? Presumably, if we can compute that function, all I've got to do is measure the inputs and attributes on a bridge, and I can forecast its performance into the future, right? And that's going to inform a lot of decisions and obviously asset management. So that's how we're thinking about bridge performance. And there's a couple ways that we can study bridge performance, right? And this is very generic. But on the one hand, you have approaches where we're collecting data from huge numbers of bridges, right? Think 600,000 bridges in the country. We're collecting some information from them. And on the other end of the spectrum, we're collecting information from only a very few bridges, but we're collecting a lot more information, right? And some of the last presentations with, the UAVs and the remote sensing, they might fall somewheres in here, right? So we've got our total bridge population, we've got, we'll call it hundreds of bridges, maybe a few thousand bridges, dozens of bridges, and then individual bridges where we can do some really detailed data collection. And so historically, there's been what I would term these two approaches to studying this problem. The first is top-down. So this is the deductive approach. This is sort of the scientific method where you say, okay, I'm going to hypothesize something. I'm going to say, I think truck traffic reduces bridge life. Then I'm going to look at data from a huge population of bridges, and I'm going to test that hypothesis. I'm going to say, do in fact bridges that have higher truckloads, do they last a shorter amount of time, right? So that would be our deductive, I'll call it a top-down approach. There is another approach, an inductive approach. This would be a specific to general, and here the question might be, what is causing this specific deterioration I'm seeing on this particular bridge, right? So I go out there and there's something bizarre happening, and I might use high-resolution NDE, I might do some load testing, I might do some sensing, I might do some refined modeling, because I'm trying to figure out why this particular deterioration is appearing in this case, right? And both of these, they're quite complementary in nature, and there's a lot of effort focused on sort of merging them right now. So these top-down approaches, right? I think everybody's familiar with the long-term bridge portal. That's one example. I was walking around some of the exhibits. There's a lot of these out there now, a lot of bridge management systems. So the typical data that gets used here, obviously NBI, more and more now element level data. Some states have been collecting that for some time. Environmental data, number of snowfalls, freeze-thaw events, et cetera. The key here is that the data really has to be available comprehensively, right? So you can't make decisions based on the data you want here. You really have to make decisions based on the data you have. And you have to have that data across large populations because the tools that you're using require lots of information. So, GIS systems, but historically these, Markov and Weibull distributions, and now more recently, different types of machine learning or artificial intelligence where you don't need to have a static model form. The model form is actually derived from the data itself, right? The price that you pay is you need a ton of data in those cases, right? So this is a great approach. I'm not arguing that we shouldn't be doing it. We should be doing more of it. But there is an inherent limitation in this, right? There's a few. One, this is just an example of some modeling that we've recently done for some states in the Northeast. And this is, the orange is steel and the blue is pre-stressed concrete. The story is they're both pretty much the same in this population. The solid line is the 50th percentile. And then we have our overperforming bridges, so our 95th percentile, and then our underperforming bridges, our 5th percentile, right? So one of the big takeaways is, boy, there's a lot of variability there, right? If I told you build a bridge today, and in 30 years it's going to be somewhere between an 8 and a 4, and I had to do modeling to tell you that, you'd say you're a moron, right? Because I can tell you that right now, right? So there's a lot of variability here. Some of that may be because of the high or sort of low resolution data we have. Some is likely because there's a lot of things that are affecting bridge performance that we're not measuring right now very well. And so these populations, even though I say they're the same, they're really not the same, right? Some were built really well and some were built maybe not so well, right? So that's part of it. But the other and maybe more fundamental limitation is that the approach taken here is to say, if I go out to bridges and I take data from bridges that are 1 year old and 80 years old, I can line them up, and that gives me a time history of how bridges deteriorate. The problem is all those bridges are different, right? So at some point we didn't use epoxy-coated rebar. Now people are maybe not going away from that. At some point we didn't have UHPC or HPC or pre-stressing or different types of steel coating, or we didn't use continuous bridges. And so bridge practice changed, right? And so if you look at a bridge that was built 30 years ago or 35 years ago, it's not the same as the bridge we build today. And yet all of this information about, you know, its service life is based on bridges that were built many years ago. The second problem we have is that you guys do a really good job of not letting bridges go to a 4, right? So if you look at the data, we see very few bridges that are 5s and go to 4s. What you see is bridges that are 5s, and they may stay 5s for a long time. I think probably there are people intervening and keeping them at a certain condition. Or those 5s will go to 7s because somebody did some minor replacement or repair. But very few bridges go from 5 to 4, so we can't even predict. We don't have that information, right? Because the bridge didn't deteriorate in its sort of natural way. There was all these interventions. So those are sort of the top-down approaches. Now the bottom-up approaches, there's a lot of them, right? And there's a lot that are being developed all the time. I would sort of group some of the UAS stuff into that, although that's an interesting example of a technology that has the potential to bridge the gap, right? The data collection, there's nothing inherently expensive about it, and so it could be done more comprehensively than individual structures now. But here, you know, if you've heard of this thumper system that does rapid modal testing to look at how girders share load and update load ratings, you might have heard of the Rabbit here, which is a bunch of different NDE technologies that get fused to provide some picture of bridge deck performance and how things degrade with time. We've done a lot with LiDAR. You can do, I'm a big fan of infrared. You can even paste it onto models. You can use HoloLens, so when the inspector is out on site, they actually see it projected on the bridge itself. So there's a lot of things that can be done. They're somewhat expensive at this point, and they've been sort of relegated to a few structures, right? They're sort of the exceptions to the rule. Where this is going, and you see it with the UAS, you see it with a lot of other things, is that right now, or historically, you could see that technologies, the use of sensing, the use of NDE, if I'm gonna double the cost of the inspection, I'll probably get hopefully double the accuracy and reliability. And as people take those technologies and they package them in a way that can easily be deployed to civil systems, we can have the potential of jumping off this curve, right? Actually doing inspections for maybe the same time and cost of what a conventional visual inspection is, but collecting a lot more quantitative data. The other perspective, and this is where I think a lot of the UAV stuff fits in, you know, state of the practice is a visual inspection, and state of the art is, you know, some crazy health monitoring system and NDE that people put on these large signature bridges, right? These can only be applied to very few bridges. These are applied to all bridges, but relatively low quantitative objective information. So there's a lot of potential ground here, right? Where I can apply it to a large number of bridges and actually collect some of this digital information, right? And the reason I want to talk about these two approaches before I jump into the lab, these top-down and bottom-up, is I don't want to say that the facility that we have now is going to replace these, right? It's going to augment these. I think both of these approaches are necessary and quite complementary, right? And in fact, you can look at the synergies between these approaches. So I'm going to say understanding bridge performance requires quantitative objective data across large populations of bridges in a timely manner, right? So top-down approaches do a great job with the big population of bridges. Bottom-up approaches do a really good job with this quantitative objective data. They're getting better here. They're always going to be getting better here. But the problem is they do a pretty terrible job for this in a timely manner, right? The same challenge that exists for top-down approaches exists for bottom-up. That is, if I want to look at how a bridge is going to perform over 40 years, I have two options. I can track the performance of a bridge over 40 years, or I can sample bridges that are 10 years old, 20 years old, 30 years old, 40 years old, and string them together, right? The problem with that is the 40-year-old bridge is different than the 30-year-old bridge and maybe different than the 20-year-old bridge, right? So this is one of the fundamental limitations, right? And that leads me into sort of this principal challenge of this slow feedback loop, right? And so if I build a bridge today and I allow it to degrade with time, over 10 years I might see some deterioration. Over 20 years I might see some more deterioration. But the feedback loop is relatively slow, right? So if I have material X, right? There's a lot of people in the exhibit hall that have great materials, right? I don't know which ones are great and which ones aren't, but there's the possibility that there's some materials that people are making available in that other room that could revolutionize bridge engineering, right? But we'd have to try them, and then we'd have to wait 20 years to go, okay, I think this one's great. You know, this one actually works. And then we're dealing with 20-year-old technology, right? So we can look at 10-year-old technology, right? That was the best cell phone of 2007, which I love because the iPhone came out in 2007. And this was the biggest breakthrough in 1997. So this is about 10-year-old technology. This is about 20-year-old technology. That's what it looks like, right? Things are moving so fast today. And it's not just in information technology, but in materials technology, right? So having to wait 10 years, 20 years, 30 years to decouple things that are potentially really influential to ones that maybe know better than what we're doing today, that's a long time to wait when technology is moving this quickly. And so what we did is, in partnership with New Jersey DOT, we've developed an accelerated testing facility. And the idea, the goal, was to accelerate deterioration of bridges in some sort of realistic manner through applying live loads, environmental, and maintenance demands, right, to full-scale superstructures. Those were the requirements. Through that, we can perform what I'll call longitudinal studies, which means we can build a structure in there and track its performance with time to try to update deterioration curves, right? So that's longitudinal. We can do comparative studies. So I can take two competing systems, whether they're, say, overlays or reinforcement coatings or different concrete mixes, and I can do a comparative study between those two, right? And then the final one is that we can decouple some of these influences. So if you think back to when I talked about structuring bridge performance, one of the problems is all those influences are happening at the same time. Live loads, environmental, there was some level of construction quality, good or bad. It's very difficult to decouple those out in real life. In a laboratory setting, we could decouple those. So this is what it looks like. It's on our Livingston campus at Rutgers. It was commissioned about 6 months ago. And so it basically has a very large environmental chamber, 28 feet wide by 50 feet long, and it can accommodate up to a 5-foot depth of a superstructure. It applies the rear carriage of a tractor trailer, so 2-axle loading, up between 10 kips and 60 kips, runs constant 20 miles an hour. We can provide precipitation and de-icing chemicals up to 18% brine. This is the big one here. We can cool this to 0 degrees Fahrenheit, so 30 degrees below freezing, all the way up to 104 degrees Fahrenheit. And we can fluctuate that temperature as we would like. And then we have a lot of control systems, high-speed data acquisition, et cetera. So the way the laboratory is envisioned to work, so the first specimen will actually be constructing in the lab, but in the future we have a yard off to the side where we can build these superstructures and bring them into the lab. So the environmental chamber and the live load beam slide out of the way, so it's sort of open to the sky. Everything's on rails, so we can close the environmental chamber. We can locate this live load beam at any location, any width along the bridge. And then this is a little bit of an old animation. The precipitation is actually on the carriage now and gets sprayed out as it's driving back and forth. But we can apply, just regular water. We can apply, again, de-icing chemicals up to 18% brine. We can cool it. We can heat it. And throughout all of this, we're running live loads, 17,500 cycles per day. Right? It's not a fatigue test, right? When you add up these cycles, we're not getting millions of cycles. But it will impose that live load together with the environmental, together with some of the maintenance demands, again, on a full-scale superstructure system. And then eventually we are going to be seeing some deterioration. And then we can track that. Sorry about the sound. The people that did the animation got a little carried away, I think. But so we can track that. We can track that with NDE. We can have embedding sensing. We can put sensors on the girders. And the idea is identify where deterioration begins and how it progresses, and then to be able to start asking the questions of what are the best repair techniques for this, and when is the best time to apply those. Right? So a couple, some of the details of where we're headed, and then I'll wrap this up fairly quickly and hopefully get some comments. There is a pooled funds study that I believe is in the works at some level, but I'm really interested in hearing ideas of questions we should be asking. As you can imagine, some of these experiments are a little bit expensive, and so the more questions we can ask and answer with every experiment, the more value we provide. So when you're looking at live load, there's a couple ways we can apply it, right? We can apply it at any location along the width of the bridge. This would be our maximum realistic deck force. This would be our maximum, I'm going to call it unrealistic deck force, where you're actually loading the overhang to maximize that negative moment over that fascia girder. Minimum deck force, right? Just applying the loads effectively over the girders themselves. And we can also examine different levels. So obviously the girders, these girders here, I'm not sure they're going to see different live load, but locally the deck would see different levels of tire pressure, right? So we can, when we're on this half of the bridge, we can keep it at a 30 kip rear carriage, and at this half of the bridge, we can keep it at a 60 kip rear carriage if we wanted. This gives us, if we wanted to look at a 1-year test duration, this gives us about 6.5 million cycles. That translates to an average daily truck traffic of almost 900 over 20 years. So this is not I-95 through Philadelphia, right, granted. But if you look at the median value of average daily truck traffic in the US, I think it's about 700, right? So this is at least larger than that over a 20-year period. Freeze-Thaw cycles, this was done in conjunction with some of my colleagues from New Jersey Institute of Technology that deal with a lot of the material level. But we're looking at a number of freeze-thaw cycles coupled with some hot-dry cycles. Apparently that can create a lot of tension with the drying, also can get some of the corrosion moving. So they tell me an 8-hour dwell time is really what's required here to freeze that outside surface where the damage occurs. So in a 9-month period, so think about 12 months here, I should have updated that, we're going to get more than 300 freeze-thaw cycles. This ASTM standard for freeze-thaw testing gives us something around 300. There's a lot of materials that will pass that. I've been told that very few will ever come out of that in pristine condition, right? So that's a pretty harsh test. We're going to replicate that sort of at the full scale. By the way, this is where the expense is. Almost now Rutgers is going to be covering the bill, at least in the near term, but almost $300,000 worth of power is required in a year to impose those cycles, right? That's where all of the power costs are. So some potential testing approaches we've talked with people with looking at different types of reinforcement. So whether it's epoxy coated or FRP or black steel or galvanized, I'd rather not look at stainless. I'm not sure we're going to learn much there. Maybe we've even talked to people that want to look at 4 different types, right, and compare them on the same specimen. Right. Looking at a number of overlay systems. So after you do some initial testing on a bare deck, come back and look at different overlay systems, right? And then we can run the live loads, effectively down there and see which of these overlay systems is performing better, if there's a difference between them. The only catch here is that the top of the bridge always has to be at the same level. So if I want to put an overlay, I can drop the bridge down, no problem, take some shims out under the bearings, but I can't have a 2-inch overlay next to a 3/4-inch overlay, right? I'd be having to move this bridge up and down all the time. So we have to manage that. We've also talked with people that are interested in looking at different steel coating systems. This is something that came out of some discussions at Federal Highway of the effectiveness of metallizing systems in this particular detail. So the idea could be, leave a joint open so a lot of the de-icing chemicals will come back and deteriorate the ends of the girders, use 4 different coating systems on those girders, conceivably look at a lot of different repair techniques, right, for girder ends as well, right? And having some slope, that's about the maximum slope we can get. The top of the bridge has to be flat. So we have to vary the haunch from 1 to 3 inches to get this 2-inch slope over 50 feet. All right, so this is my last slide, and then if there's time or interest, we can hopefully have some questions or discussions. But this is something we showed before, but I'm adding accelerated testing here, right? And it's not perfect, right? There's a number of challenges we're going to have, right? One is balancing this, right? I can throw 18% salt on this all the time, and we get deterioration probably pretty quickly. Whether that's representative of what happens out in real life, I would argue is probably not. So being able to balance these different inputs and get realistic deterioration is going to be a challenge. We have to be honest about that. But it also provides a lot of value. One, we can get really good quantitative data. So I can instrument this from construction, look at intrinsic forces that are generated in the deck, not after the fact where I go and put a sensor on and I don't measure what sort of stress state is the deck in after it cures, right? That could be a pretty good indicator of long-term performance perhaps. So we can do a really good job there. We can also do a much better job for this in a timely manner, right? We are never going to do a good job across a large population of bridges, and that's where effectively a group of different approaches, I think, are required, right? And so now I would argue we should read this column downward. So understanding bridge performance requires all of those approaches because that's where we're going to pick up these sort of, at least one in each of these columns.
You mentioned there towards the end, you mentioned putting 15% or 18%, salt on there and seeing what happens. I would be interested, coast to coast, there are very different philosophies on salting bridges, both from a structural preservation standpoint and environmental standpoint. To me, it would be really interesting to see what kind of bang for our buck are we getting out of salting bridges, and where is the kind of the break-even point between seeing a real effect on corrosion of our superstructures from the de-icing salts, how much salting is too much? How much are we going too far in some states, and can we back off? And is there a minimum level that we can use in some states that are more averse to that we can get a lot of benefit from it and maybe not see as much deterioration as we think we might see? Right now the thought is it's either a yes or no, but is there an in-between that the whole country can use or regions can use to make more sense?
Yeah, no, that's a good point. And a lot of people have suggested that we try to look at different de-icing agents, and maybe put up a barrier. So split this thing in half and put up a barrier. And on this half we use one type, and on this half we use another. And we look at the effectiveness, both in terms of, keeping the surface from not freezing at least down to, let's say, 25 degrees or so, and then looking at long-term deterioration. So that's an option. I do think that, I'm working with another faculty member who is interested in creating a concrete that will not freeze below 25 degrees. So the water on it won't freeze. There's a latent heat in it. The problem that I had with that is, whether we salt our bridges or not, if people are salting the roads, it's on the bridges, right? So, I think there's a lot of people that are thinking that we can turn off salt as we go across bridges, and cars aren't going to carry it on. So I don't know how much control we have, particularly when it's really a traffic safety issue. In Philadelphia, I'm going to say about a year and a half ago, they didn't put salt down fast enough on one of the bypasses over the northern area of the city, and there was like a 70-car pileup. I mean, and I think they see that, and maybe rightly so, they're going to err on the side of traffic safety, and we're going to manage things with the deterioration. But you make a good point.
I was wondering about temperature gradients. So are you thinking of using heat lamps and doing anything to look at the thermal differences?
At this point we weren't. Now we have, so the way the bridge deck is, it almost completely covers if we do the full 28-foot width, it almost completely splits the lab in half. And we have a heating system on top, and we have a heating system underneath. So conceivably, you could impose a temperature gradient by turning the top one up to 100 degrees, leaving the bottom one at 60 degrees or something. I think for the first set of experiments, at least for the folks that I've been talking to, the thought is let's do simple first. The one thing that I think we're going to run into here, which could conceivably be a problem out in real life, is not just the temperature gradients, but the difference in temperature of the steel and the concrete. So as we all know that steel and concrete have very similar thermal expansion coefficients. However, they have very different thermal mass. And so when a temperature is changed, the steel assumes that temperature almost immediately. And it takes a very long time for the concrete to assume that temperature. And so even if they have the same coefficient of thermal expansion, the inside of a deck is a different temperature than the steel girders that it's sitting on. And so they are fighting each other. And for any people that have gone out and put strain gauges on bridges, you see this. Sun comes up in the morning, and you get huge stresses, maybe larger than most of the live load stresses you'll see. And I don't think that's just the temperature gradients. In a lot of cases, it's the steel girders, that can be hotter than the deck. Obviously, the top of the deck is hotter, but the deck is, really insulates itself. So I think in the near term, we're not thinking of gradients. It's possible we could put heat lamps in there, but it wasn't something that we thought about initially.
I had a question on the pull study, but I just wanted to respond to the salt question just very quickly. I was doing a presentation for a local county DOT, and we were talking about the salt problems on the bridges. And their DPW guy was in the room, and he said, obviously the biggest problem with controlling salt on bridges is the fact that there's the human factor to consider, that the guy who's in the salt truck in the middle of the night doesn't have the chance to respond that quickly. And one of the other guys said, a lot of the contractors are deathly afraid that a lot of the vehicles that they use are dump trucks, and they need to raise the bed in order to get the salt to the back of the truck. And there's been a lot of instances where people have raised the beds going under bridges and they've hit bridges. So now these guys know that the safest way to do that is to raise the bed when you're on top of a bridge. So a lot of times when they do that, a lot of the salt will spill out over the back of the tailgate onto the bridge deck, which creates an even bigger problem. But my question is, we were talking at the Northeast Bridge Preservation Conference, and you had mentioned the pool study back then. So I know a lot of the manufacturers at the time were interested in getting involved in that pool study. So I'm wondering, since then, has there been any update on that pool study, and where does that stand at this point?
So I think I think the best place to go, and I could get a contact for you, would be New Jersey DOT. I believe they're going to lead it. So my understanding is they have initiated that process. I believe it's been approved by Federal Highway. They haven't put an RFP out yet, which I think would be the next step, and then we would have to respond to that. But I would look probably within the next few months, hopefully. I've been waiting for this for a long time, but in the next few months, I think once some of the contractual issues are done, that should open up on, I think Federal Highway has a website where you can see the open pooled fund studies. I think it should probably be available there at that point.
Led by Federal Highway or by New Jersey DOT?
I believe it's New Jersey DOT. So thank you.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.